Assalamualaikum and good morning everyone. Welcome to our technical group discussion. I'm Honorable Kis Binti Hairulizam, B0922101175, and along with my teammates, we will be exploring important topics related to the structural integrity and strength of ship. These include ship types, failure mode, longitudinal strain, pressure effect, and structural design. Let's begin by introducing everyone.
So, hello there everyone. My name is Muhammad Aiman bin Hanis, number matrix B0922100077.
Hello there, good morning. My name is Mazlan Nixon. My metric number is B09221-231. So today, I'm introducing myself as a presenter today along with my teammates.
Hello, my name is Aceh Daniel Melvin Mojinga, matrix number B0922100088, and I'm going to be one of the presenters also. So,
hello everyone, my name is Shamina Jira binti Omar and normal metric is B0922100054.
So Aiman, can you share with us the different type of shapes and how their strength is considered during design?
Alright, thank you Balkis for this kind of opportunity. So, I will briefly explain about the three types of common type of ship. So, there's cargo ship, of course, there's tank ship, and lastly the naval ship. And how their structural strength is considered during design stage. So first we have cargo ship. So cargo ship is such a container ship, a bulk carrier. So these ships are designed to carry multiple types of dry goods like container, coal, this one is coal or grain. So because they are long and carry a heavy load, they require a strong longitudinal strength. This helps them resist hogging and sagging, which happen when the ship move over wave to strengthen the hull. Designer use reinforced deck girder, and double bottom structures. So next we have the tank ship. So the second is the tank ship. For example, like oil tankers and LNG carriers. So these ships are built to transport a large volume of liquid cargo. So the main design challenge is handling those internal pressure from the liquid inside the tank. They must also resist sloshing effect, which is movement of the liquid that can affect the balance and the stability of the ship. So these ships are designed with a strong internal bulkheads and compartmentalized tank to distribute the load safely. And lastly, the common types of ship that available globally in the world is naval ship. So third, we have a naval ship such as frigates, corvettes, and submarines. So these are military vessels designed for combat, patrol, and defense mission. Naval ship require high structural strength and flexibility, especially to survive in harsh sea and combat environment. So they must be withstand shock load from nearby explosion and high-speed maneuvering forces. So designer also prioritize weight optimization for speed and stealth, while ensuring strong watertight integrity to resist damage during operation. So of course we move on to the common structural strength factors. So across all ship type, there are several key strength considerations. These include longitudinal strength to resist bending, of course the transverse strength to resist wave pressure from the sides, and lastly the torsional strength to prevent twisting, especially for a long or wide ship. So these materials are usually marine grade steel or aluminum, and all design must follow safety from classification societies such as ABS, DMV, or Lloyd's Register. So to sum all of it, cargo tank and naval ship are designed based on their unique function, and structural strength plays a vital role in ensuring their performance, safety, and durability at the sea. And that's all for my discussion. So Mazlan, we obviously know that ships operate in extreme conditions. So what are some failure modes that we need to be aware in a ship structure?
Good question, Aiman. So, there are many modes failure of the ship, but I will explain briefly about the modes failure. So, the firstly is the fatigue failure, the second is corrosion, the third is buckling, fourth is fracture or crack propagation, the fifth is the welding defects, the sixth is overloading, and seven, grinder failure, which is global structure failure, and then impact damage, and the 9 is fire and thermal damage, and the 10, the finally vibration, which is the induction damage. So I will simply brief about the factor of the mode failure of the ship. So the first one is the fatigue failure, which is its repeated cycling loading from waves and vibration. For example, cracks developing at weld joint or sharp corners over time. So it may lead to sudden failure even at low stress level after long use. And then the third one is the buckling. So which is we are more focusing on this mode failure, because of our group discussion is explaining about the structure of the ship. So buckling simply it's a cause of comprehensive loads from cargo, hydrostatic pressure, or collision impact. It's vulnerable areas. Its effect on hull plates and stiffener and the bulkheads. It's risk for the sudden collapse of the structural components. So finally, I will brief about the fracture, which is the crack. It's caused the stress concentration and sharp notch or welding defects. So it will lead from buckling and it will become a fracture on the structure. And then we move to the formula, which is the longitudinal stress, because the buckling mode of the structure ship it's happen from the forward and the aft of the ship. So it will affect our longitudinal, which is the longitudinal coefficient formula is water plane area divided by length of the ship times breadth of the ship. So it will cause the buckling mode inside our structural ship. So I will explain briefly about the fogging and sagging force direction. So I will explain about firstly I will explain about sagging force direction. So let's take an example of this. This is our longitudinal of our ship structure. So the sagging it will happen because it's compressed in the middle of our ship. So which is it will affect our midship length from here to here, up until here. And then the force will stretch upwards at the aft and the forward of the ship. But it's contradict with the fogging. It stretch the force at the midship. It stretch upwards, but the force between at the aft and the forward, it will compress simultaneously. So it will become the arch, like a bridge. So that's my explanation about modes failure of the ship. So Archer, can you explain about the more detail about longitudinal stress?
Good question, Mazlan. I think that longitudinal strength it refers to a ship's ability to resist bending along its length from the bow to the stern. Ships can actually bend, especially when they are floating on waves. Like, for example, when a wave crest is in the middle of the ship, it tends to drop down. That basically means it's called hogging. But when the wave is under the bow and stern and the middle sags, that's called sagging. These conditions cause the ship to bend longitudinally. I would say, for example, if the ship doesn't have enough longitudinal strength, it could suffer structural damage, or in the worst case, even break apart. This is particularly important for large vessels like tankers or container ships, which are more suspectably due to their size. The parts of the ships that contributes to longitudinal strength include the keel, the deck, the bottom structure, and the longitudinal bulkheads. These components work together like the flange of a giant beam, providing resistance to bending forces. Furthermore, it ensures sufficient longitudinal strength. Is a fundamental aspect to ship design. Naval architectures must analyze and verify it using structural theory and specialized software tools. Remember, the ship isn't just floating, it's constantly flexing with the sea. That's why longitudinal strength is so important. But enough for me. Shamin, ships carry heavy fluids like oil and also face water pressure from the sea. How do designers account for these pressures on the hull?
Thank you, Aceh, for the great question. So, today I want to explain how ship design account for the pressure acting on a ship hull, especially when carrying heavy fluid like oil and when exposed to sea pressure. 1. Understanding the pressure. There are two main types pressure acting on the ship hull. First is external pressure from the oil stored inside the cargo tanks. Second, external pressure from the sea water outside the hull. Second, hydrostatic pressure calculation. When a liquid oil is stored in a tank, it exerts pressure on the wall and bottom of the tank. The formula for hydrostatic pressure is pressure equal density multiply gravity multiply depth. 3 is designed to withstand internal pressure. To handle this internal pressure, ships have a bulkhead with an internal wall that divide in the tanks. They use stiffeners and support inside the hull to prevent bending and crack. For oil tanker, a double hull is used for extra protection in case of leak or collision. 4. External sea pressure. At the same time, the ship also faces external pressure from the sea. This is especially strong at the bottom of the hull or during rock weather. The hull must resist this pressure without deforming. Designers use finite element analysis, a type of computer simulation to test how the hull will respond to waves, sea load, and impacts. 5 is material selection. The material used the ship must be strong and corrosion resistant. Most ships use high tensile steel, which is strong and flexible. Special coating had the protect against rust from seawater. And the last is safety regulation. All ships must follow strict rules from international body like Register or American Bureau of Shipping. The ensure the hull can handle more pressure than expected, called a safety factor. Regular inspection and maintenance are done, and all material design meet international standard. So, Bakis, what are the main type of structure system used in a shipbuilding?
Good question, Shamin. So let's begin with the most important part of any ship, the hull. The hull is the main body of the ship, and it's what keeps the vessel afloat. It includes the outer shell, which is called the shell plating, and the internal framework that gives the ship its strength. The hull is designed to resist external forces such as waves, water pressure, and wind, while also supporting the weight of cargo and the ship itself. Running along the bottom of the hull is the keel, which acts like the backbone of the ship. It provides a longitudinal strength and helps keep the ship stable in the water. Attached to the keel are frames, which are like ribs that gives the hull its shape and support the outer plating. Above the hull, we have the support provides longitudinal strength and help keep the sail stable in the water. Attached to the keel are fins, which are like ribs that gives the hull its shape and support the outer plating. Above the hull, we have the superstructure. We This include everything built about the main deck, such as the bridge, accommodation area, and navigation equipment. The superstructure is important not just for housing the crew and equipment, but also for maintaining visibility and control of the ship. Another critical part of the ship design is the double bottom structure. This is the space between the inner and outer bottom of the hull. It serves multiple purposes. It adds extra strength to the bottom of the ship, provides the safety buffer in case of running or collision, and is often used to store ballast water, which helps balance the ship. Inside the ship, we also have bulkhead and decks. Bulkheads are vertical walls that divide the ship into the compartment. These compartments are usually watertight, which means if one section floats, the other remains dry. Next, on the other hand, horizontal platform that divide the ship into different levels. They provide space for cargo, equipment, and crew activities. Now, let's talk about longitudinal and transverse structure. Longitudinal structures run along the length of the ship, while transverse structure run across its width. Together, they form a grid-like framework that distributes a load evenly and prevent the ship from bending or twisting under stress. So different types of ships also have a specialized structure. For example, tankers have reinforced tanks to carry liquid cargo like oil and chemicals. So these tanks are separated by cofferdams to prevent leaks and contamination. Container ships have strong sail guides and hatch cover to secure containers during transport. And naval ships often include armor plating, shock-resistant compartment to withstand combat conditions. Finally, let's briefly touch on the materials used in ship structure. Most ships are built using steel because of its strength and durability. However, aluminium is used in high-speed vessels to reduce weight, and composite material are becoming more common in smaller boat and advanced naval application.
So, yeah, in conclusion, the study of ship types and their structural characteristics is fundamental to understanding maritime engineering and naval architecture. Ships are designed based on their specific purposes, such as cargo transport, passenger movement, oil transportation, or military operations. Each type, be it container ships, tankers, bulk carriers, Or warships comes with distinct structural demands that directly influence their design, material use, and layout. Recognizing the functional differences between ship types sets the foundation for understanding how and why ships are built in particular ways.
So, an essential aspect of ship design is its structural strength, which determines its ability to withstand harsh marine environmentals, and operational loads. The strength of a ship is influenced by both its global structural integrity and local reinforcement. Factors such as the hull material, framing system, and longitudinal members contribute significantly to its strength. Proper structural planning ensure that ship can endure the complex combination of static and dynamic forces to encounter at the sea without deforming or failing prematurely.
However, ship still prone to various modes of failure if improperly designed or maintained. These modes including a buckling, a fatigue, corrosion, and fracture due to repeated stress or extreme environment forces. So understanding this potential failure allow engineer to incorporate preventive measures such as stress distribution, of course, the corrosion resistant material, and fatigue analysis in the design phase. Emphasizing failure modes is essential to ensure both of the safety of the ship to and the life on board.
Among all structural consideration, the longitudinal strength of ship hold particular importance. Since ships operate in dynamic waves environment, they are subjected to many moments that can cause sagging or hogging. Reinforcing to longitudinal structure using continuous stacks, double bottom, and a strong longitudinal stiffness is crucial to maintaining structural continuity and preventing structural collapse during operation.
Lastly, external pressure such as the form, water, and oil exert concern lot on the ship crew, which emphasizing the importance of robust ship structure. The ship must be capable of withstanding hydrostatic pressure when submerged and internal pressure in compartments storing oil or fuel. The choice between frame structure, longitudinal system, and combined framework directly affect how this pressure is exerted. By integrating infrastructure type with consideration of load and pressure dynamics, ship can achieve optimal performance and safety